answer. Okay, now let us see the evaluation results of TPU version 1, which is from this paper. The presentations I have made, they are mostly from this paper. Here we have, so the CPU I was talking about was this CPU and this GPU, and this is the TPU. So here the area of TPU is just half of the CPU. This is a process node, 8 nanometer. Frequency, CPU uses very high frequency. CPUs are well known for that. Here the frequency is very low. So this is at the die level. Now the TDP is very small, just 75 watts. And in fact, out of this is the peak, theoretical power consumption, but actual power consumption is just 40 watts, which is really commendable. Here it is 145 watts. In GPU it is 150 watts. Now here Haswell has support for 8-bit, but it's very poor performance. For floating point also, its peak performance is not very good. Here the peak throughput is very high, 92 teraops per second. Okay. And here it has no support for floating point. And here this is the memory bandwidth. This is the key limitation of TPU version 1, as we'll see later on. So GPU uses high bandwidth memory such as GDDR, that's why it has high bandwidth. CPU does not use high bandwidth memories, that's another bottleneck. And on-chip memory, CPUs use a lot of L1 cache, L2 cache, and so on, whereas the K80 here doesn't have a lot of on-chip memory. And here it has 28 megabytes of memory. And the same thing now extended to servers. So at the server level, we have multiple dies, which has total much higher TDP. Okay. So before we discuss the result, let us discuss their evaluation, their limitation first. So TPU uses int8, whereas Xeon CPU uses FP32. Although if they had ported the code to AVX2, that would have improved CPU performance by 3 to 4 times. K80 GPU also lacks int8 support. There are other recent GPUs which provide int8 support, such as Volta tuning, and they have also enabled ECC in the GPU. So if they disabled it, performance could have improved. So these are the benchmarks. They have used 6 out of them. One is rank plane, one of them is LSTM, one CNSR inception, DeepMind AlphaGo. Here are the weights, number of weights. Now, if you attended last week's lecture, so this is arithmetic intensity. Arithmetic intensity is highest for this CNN, and it also does mean a lot of weights. So as you can expect, this will give the highest performance. Here, arithmetic intensity is very poor, so this will give very low performance. And here, how many of the deployed TPUs run these workloads? So very few run CNN. So at least at that time, CNNs were not so popular, at least in Google's data centers. And here, these are the nonlinear function used. Here, these are sigma 10H. These are the total number of layers, and the number of lines is not very large. These are somewhat small programs. So CNN 0 has the highest ops by byte ratio. That's why they are compute bound, and LSTMs are bandwidth bound. LSCNS and MLPs are easy to parallelize. LSTMs are difficult to parallelize. LSTMs have dependency across the steps, so that's why they are difficult to parallelize. That's why there's not so much research on hardware accelerator for LSTMs, whereas for CNN and MLP, much more research has been done. So here is the result. So 92 is the peak performance. That means this is the roof line. This is the best you can do. Now, out of the 92, how much is the actual performance? So for the CNN 0, as I said, the performance should be highest. So here, performance actually comes out to be highest, 86. For CNN 1, it is just 14. And for others, it is much less. For LSTM, it is just 3 or 2. So the reason for this is, for CNN, you are not stalling much. For CNN 0, you are not stalling much due to memory. As I said, the bandwidth is very small. That's why you are always stalling for the memory data to arrive. But for CNN 0, because first of all, the arithmetic intensity is so high, and even the number of weights you need to read is very small, so you don't need to stall a lot. Whereas here, CNN 1, you have unused megs are too much, and useful megs are only 22%. So that's why the performance comes down. So as a hardware architect, if you were to join this company, by seeing this figure, you know where to optimize. What is eating up your performance? So here are the results. So here we have MLP, LSTM, Siemens. This is the weighted average based on Google's workload mix. So TPU is much faster than CPU and GPU for MLP and Siemens. However, CPU is very reasonably good for LSTMs because the CPUs are good for those workloads which have medium parallelism. And CPUs are good in hiding the latency. So if you have irregular workload where you can't parallelize, then CPU will come out to be best. But GPU and TPU comes out to be best where you have possibility of doing parallelization. That's why for Siemens and LPs, TPU comes out the best. So compared to contemporaries GPU or CPU, TPU is 15 to 32 times faster, 15 to 30 times faster. And performance per watt is 30 to 80 times higher. So the bottleneck of TPU version 1, let us understand, it uses DDR3 memory, which is low bandwidth. If they were to use high bandwidth memory, which is HBM or GDDR5 or 6, TPU could be improved even further. Okay. So now you see the scope for improvement, and that's what we have done in the next version.